right. Hello, everyone. My name is Haozhe Zhang. I'm a postdoc at University of Zurich. And today I'm going to give a short introduction to the recent advances in incremental view maintenance. So let's first define the problem incremental view maintenance, or IVM for short, trying to solve. So given a database, a dynamic database, and a query, we want to maintain the query output under updates. So the updates can be tuple insert or delete. Why we want to solve such a problem? In typical data processing scenario, we normally have some small change to the query input, and they will lead to some small change in the query output. Right? It doesn't necessarily to be the fully materialized output, but it can be the representation of the output. So the naive approach to reflect the change is to recompute the query output from scratch. But this can be inefficient because the input data can be very large, and if you compute from scratch, it can be expensive. So the more preferred way to do it is to use IVM, which is to propagate the change from the input to the output. That is, we only compute the changes that are triggered by the update. Because the change is normally much smaller than the original data, so this can be much faster. And theoretical results shows IVM can give lower complexity than recomputation, and there are also runtime improvement reported for practical workloads. So let's look at a warm-up example on the maintaining of a triangle count on this IVM problem. So assume we have a database with these three relations, R, S, and T. They have this schema A, B, B, C, and C, A. And we want to know how many triangles are in this database. So we use the semantic. We consider these relations as functions mapping from tuples to count. In fact, we can also map them to more complicated things, anything in a ring, but here we use count. For example, in R, the first tuple A1, B1, it has the count 2. It means this tuple A1, B1 appears twice in relation R. So we want to understand how many triangles are in this database. So for example, here these three blue tuples A1, B1, B1, C1, C1, A1, they form a triangle, which is in the result A1, B1, C1. And the number of triangles they contribute is 4, which is because there are 2 A1, B1 in R and 2 B1, C1 in S and 1 C1, A1 in T. So in total, there are 4 triangles contributed by these 3 tuples. Similarly, we can compute the triangles contributed by the other tuples. And in the end, we sum these counts together to get 19. There are in total 19 triangles in this database. And this is formulated as the formula there. We do the product of the 3 relations and sum over their variables. So this is about computing the triangle count in the database. So what about updates? Assume we have an update to relation R, either an insert and a delete. We represent it as a delta R there. We use positive or negative values to represent insert or delete. Here we have update to R with A2B1 with -2 count. It means we remove 2 A2B1 tuples from relation R. So that means we need to update that tuple in the original data, and we update its count from 3 to 1. So the naive approach is then to recompute the whole thing here and to get the updated result. But actually, we can just compute the change change triggered by this update. So we need to update. We see this right tuple A2B1 is joined with these 2 blue tuples in S and T. So we can update the corresponding tuple in R times S times T. update its count from 9 to 3, and consequently update the final query result from 19 to 13. So this is the idea of IVM. We try to minimize the time to reflect update. So in this talk, I will mainly focus on the fine-grained complexity and optimality of IVM for conjunctive queries. Theoretical results are made in the past decades. They aim to mirror the development of worst-case optimal join algorithms, which were developed for static databases. And these results guide the development of some new IVM engines like dbToaster, Dynamic Inakaki, FIVM, cron, and the IVM system in relational AI. And they yield lower complexity, and also experiment results show they have faster runtime than classical IVM. And each of these reported advancements is a small increment, but together they pave a way to a deeper understanding of IVM. So let's take a closer look at the IVM problem to understand the different complexities we are interested in. So assume we are given a query and a database. We have this pre-processing step, which is we use this time to compute some data structure that represents the output. This data structure does not have to be exactly the fully materialized result, but it should allow us to enumerate the result efficiently. Whenever the user gives an access request to the result, we should be able to enumerate the result, every tuple in the result one by one efficiently. And the time for enumerate every record in the answer is called the enumeration delay. Then when they are updated to the input database, we want to update also the data structure to reflect the change. And the time to do this is called the update time. So we are interested in this three time: pre-processing time, update time, and enumeration delay, especially the update time and enumeration delay. And we want to know which IVM workloads admit the best possible maintenance. Best possible maintenance here means constant update time and constant enumeration delay, and how we can achieve them. So this question is already answered in the paper in POS 2017. So they defined the class of query named Q-hierarchical queries, and they proved that this is exactly the queries that admit the constant update time and constant enumeration delay. They show that every query that is not hierarchical cannot achieve such complexities based on the OME conjecture. Now the question is how we can achieve the complexities for Q-hierarchical queries. And the short word is, the keyword is factorization. So these Q-hierarchical queries, they have this nice property that the variables in the different relations, they have this conditional independency. And to fully exploit such independency, we construct the factorized representation of the query output. So instead of the fully materialized output, we use the factorized version of it. And such factorization admits constant delay enumeration. So we can enumerate the result as if it is already materialized. And at the same time, this factorization is more succinct, so we can update it more efficiently. There are several systems use this idea. One example is the factorized IVM, FIVM. It factorized the query output as a tree of materialized views. So the result of the query is distributed in this tree of views. And some other systems, they also use this variance of view trees. Let's see an example how this works. Let's consider this Q-hierarchical query, which is the join of RAB, SACD, and TACE. And we have the free variables ABC. That is, we want to enumerate the ABC tuples in the query result. So for Q-hierarchical queries, we can construct such a variable order. A variable order is a tree of variables, and it serves as guidance how we process the query. It must satisfy some property, but we know for Q-hierarchical queries, we can always find the variable order such that every relation is exactly a root to leaf path. Right here, RAB is root to leaf path, and ACD and ACE. Having such a structure, so variables on different branches, they are conditionally independent on their ancestors. For example, here B and C, they are conditionally independent on A, and D and E are conditionally independent on A and C. So variables on different branches, they are processed independently, which means which can lead to lower complexities. So Q-hierarchical has such a property, and factorization tries to fully exploit this. Here is how we can do it. We can map this variable order to a view tree, a tree of views. So each view is constructed from its children, and it's either by projecting away one variable, or it is the join of its children. For example, here, this V prime E is constructed by projecting this E away from T, and VC is constructing by joining the two child views, VD prime and VE prime. The constructing of this view tree can be done in a linear time, can be done in a time linear to the size of the database. So for those views that require joining the children, which are the VA and VC, which are the two views here, they can be constructed by just joining them, which require linear time. We just iterate over one view and do the join in the other view. And the other views are just by aggregating away some variables, so we can construct them in linear time by iterating over the views. So overall, all these views can be constructed in linear time. Then it's about update. Assume we have an update to a single tuple update to relation R with the given value A and B, their delta R there. We compute what are triggered by the change triggered by this delta R all the way along to the root. So here, this VB, we compute the delta version of it, V prime B. It is by projecting away B, this should be B, from the delta R. Because it's a single tuple update, it can be written as just do a lookup in the view. So this is a constant update. Then we can construct the delta for the root view VA, and delta VA can be constructed by joining this delta VB prime with the V prime C on the other side. So we propagate this update all the way up to the root. This is for update to relation R. If we have update to relation S, we can propagate also from here all the way up to the root. So for the view V prime D, we compute the delta of it by just doing a lookup. And then for this, we need to do a lookup in the V prime E, and similarly all the way to the root. For each updated view, our relation, we compute the delta of it and apply it to the original to get the updated view. So in the end, we have an updated view tree that corresponds to the updated query result. For Q-hierarchical queries, every update requires only a constant number of lookups or projections in the view tree. So that's how we achieve a constant update time for this view tree. And then for enumeration delay, another property of Q-hierarchical is we need the free variables, which are the variables that are in the results they should be connected at the root. So for this one, we have the free variables A, B, C. They are connected at the root, which means in the corresponding view tree, these variables, they are stored in the views that are connected at the root. So by constructing this view tree, remember for each view, it's computed by the child views below. So it is calibrated top-down by construction. That means every value in the root, it must appear in the views below. For example, here, so to enumerate the ABC tuples, we can start from the root view. We get the first A value, let's say A1, and then we get the paired B value in the result from relation R there. We get the B2, B3, those values for this given A1. And then we can get the C values paired with this A1. And we just concatenate them together to get the final result of ABC values. Once once these BC are exhausted, we move to the next A value A2, and similarly we can construct the ABC tuples. So this is how we achieve the constant immersion delay. This is guaranteed by the property of hierarchical queries, Q-hierarchical queries, where the free variable values are connected at the top of the view tree. So, so far we talked about the Q-hierarchical queries, but it might sound not very useful because it's only for this class of queries. But actually, many non-Q-hierarchical queries, they also behave like Q-hierarchical queries when we have more information about the data or the update sequences. So for the definition of Q-hierarchical query, only talk about the structure of the query, the schema of the database. But if we know also about the data or how we do the update, we know more. So for example, here, if we know more about the query structure, like this cascading Q-hierarchical means if we have multiple queries, we want to maintain them simultaneously, we can reuse the result of one query to help the maintenance of other queries. And together, actually maintaining multiple queries becomes easier than maintaining them one by one. And the maintenance of all these queries, they behave like they are a single Q-hierarchical query. And for data structure, if we know some like functional dependencies in the data, then there are more queries can be considered as Q-hierarchical query. Or if we know some relations are static, we can actually, again, consider them as Q-hierarchical. And if we know integrity constraints about the data, more queries are hierarchical. And for the update structure, so for update, insert only, we have shown that insert only is actually easier than the mix of insert and delete. So if we know the update sequence, it's just insert only, more queries are Q-hierarchical. And for the enclosedness of update sequence, if we know in the advance the pattern of the update, like windowed stream or our first in, first out certain patterns of insert, certain patterns of update, we know we can characterize more queries to behave like Q-hierarchical queries. So that's about the things we are doing and the result we achieved so far. So Q-hierarchical is important because for IVM problems, constant update time and constant immersion delay is important. And this gives a big picture of what we achieved so far. Okay, that's all.
Thank you. Questions?
Yes.
So you keep mentioning this term Q-hierarchical. Can you give us some intuition?
Yeah.
What are they?
So Q article is defined by both. First, it is a hierarchical query. Hierarchical query means we can, given a query, we can construct a variable order such that every relation, it is exactly a root to leaf path in the variable order. And property Q there means the free variables needs to be connected at the root. So that's an example of it.
Does sparsity come into play in the data structure in here?
Yeah, this factorization is actually trying to exploit the sparsity of the data or the independence of the data. Because Q article has this property makes sure the data has this independency, and factorization tries to exploit it. That's the sparsity here.
Okay, good. Thank you.